Okay, I believe we're in the 13th week. This is definitely our first class meeting of the week, um, and we're gonna continue working in this expanded crop model. We have in our most recent lab and discussion talked about adding dealing with the differentiated labor in this model. Now we're going to leave that aside and assume now again go back to the assumption that hired labor and family labor are perfectly substitutable, because we're going to take a different tactic here moving through this model and do more of a classic parametric programming example. We'll do the examples right out of the chapter 4 of Kaiser and Messer, and see how that works and how we might implement those, both in a spreadsheet and then in GAMS. And then I'll give you a couple of tasks and maybe a couple of hints here at the end to complete this lab. So remember, we are building this information all up from budgets, right? So line by line allocations, where possible, direct allocations to an activity, to a enterprise. And so I believe the column above this is the cutoff of the bottom of the budget. Corn, soybeans, and wheat. And so we had these yield and price assumptions that build out the revenue side of this model. And then collectively we had the allocated costs. So all the costs before labor included made this 191, 190.75, and 170 and a half. And then if we did allocate, if we took the unallocated and allocated, so the unallocated were the activities that occur, or the preparation activities that occur prior to choosing which crop you're going to make, that includes disking and plowing, then we end up with these being the relevant gross margins for our model. So 171, 170.75, and 150 and a half, right? So there's $10 of disc, $10 of plow included there. So if we were going to compare these gross margins, we compare them here, but because the unallocated applies generically, right, the margin, the cost margin, doesn't change between here and here. And then remember, we have labor constraints in the model. We have quantities of labor to be allocated, so the gross margin including labor would not be proper for our modeling work, because we're going to let the optimization choose. Okay, so this is the one part. So these yields and their prices are the part we don't have in the model yet. We haven't actually built that version of the model yet. And let's just remember our sequence. So plow to disc, then disking. Once you can disc land once it's been plowed. You can then plant, choose which crop you're going to plant to once land has been disked. And then once you've planted, you can only harvest if you actually planted that crop. If you harvest a crop, you actually generate B bushels, not acres of the crop. So those acres of harvest land get converted to the total acreage harvested multiplied by some bushel factor, right, the yield per acre, and that's what you end up with. And then when you get those bushels, you could potentially sell to the market, spot market return, store it or feed it, and do this all in sequence, right? And so the linear programming model should obey these requirements that everything has to be done in the proper sequence. There's no allowance for storing bushels that haven't been generated somewhere in the model, and the only way we have to generate them right now is through this entire sequence from plow to disc to plant to harvest. We've talked about storing and feeding, which would expand the model into some other marketing or production enterprises, but we're not going to use those, so leave that aside for the moment. And this is the full disaggregate model in the Kaiser and Messer chapter 4. So we've seen plowing, disking 3 planting activities for different crops, the harvesting activities for corn, soybeans, and wheat. You can hire some labor in, right? There's also family labor endowed to the farm or to the modeled enterprise here. And then we have 3 activities we haven't talked about yet: the harvest, sale of corn, harvest, sale of soybeans, and harvest, sale of wheat. Okay, so these are added on, and what's going to happen is you take the planted corn acre, you add the activity of completing the harvest, and then when it moves to the market side, so you take up the crop off of the harvested acre, and then when you move to the activity side of marketing for selling, this HSC, then the bushel quantity gets is available. Okay, so we'll see how that works. Yeah, so I guess just be clear, the last letter here is going to indicate the crop. So it's a little awkward because they use HS for harvesting soybeans, and then all 3 of these start with HS, which sometimes makes you think the 3rd letter could be an additional. At least it makes me think that. So I'll be reminding myself at least as we talk through this. Okay, so the tableau form of this model, we had everything up to here except the harvest, corn, soybean, and wheat before were gross margins. It took the $100 of cost up to this point, and we subtracted off, the $100 harvest cost, the $60 plant cost, the 10 and the 10, we took those off, and then we just added in the revenue. But now we're going to say when you harvest this corn, you take on $100 in cost, you use up 1.48 hours of labor, and you generate in this transfer row here 135 bushels of corn. And then the harvesting activity, the harvest sale of corn activity can then use those up. So they have to be generated first by the harvest of corn, and then they can be used right there. Okay, so equations 3 through 5 are the sort of inserted equations to deal with this marketing activity. They are balance equations or transfer rows that set the yield off of the harvested acre at some constant amount, 135, 45, or 65, depending on the crop. And then each of these, this is the per bushel price. So when you market a bushel, you get 260 here, and you'd use up one of the 135 that came off of the acre. Okay, and so that's how we would directly get this in there. And of course, the benefit here is we have the crop price assumptions directly built into our spreadsheet model. Okay, so we're no longer saying how does a change in the gross margin affect allocations. We are in the sort of parameters that that we tend to talk about, the pricing parameters, right? And when you get a forecast, they tend to be forecasts for these prices. Okay, this is what the spreadsheet looks like. So I just took the I took this tableau and put it in a spreadsheet directly. Okay, and so nothing wrong with that. That should work. If you can see everything here. This already has the solution in it, but I also have the spreadsheet. So let me pause and pull that up. Okay, so I have this scrunched down a little bit. But if we were to just cycle through here in the spreadsheet with no, these are the choices, these are the left-hand side, these are the limits, the right-hand side. We could say something like, I want to sell a bushel of corn, and it would say, okay, you sell a bushel of corn, you get $2.60. Well, I have a violation of the constraints, And so we would move down to the constraints and see that you need to harvest some corn first, right, to generate that. And so we could say that we're going to harvest 135th of an acre of corn, which generates that 1 bushel. We are back to balance on that constraint. We are going to violate another constraint when we do that, though. If I'm not mistaken, so this value may be too low to show up on the right-hand side here, but there's no way to harvest without having previously planted, right? So if we looked at the land, at the transfer row down here, we would see that we're in violation. And I don't want to keep doing this with fractions of acres, so I'm actually going to say, let's just say that we harvest an acre of corn, and instead of saying we're only going to sell 1 bushel off of it, we're going to sell every one of those. So let's just put 135 there. Okay, so we sell 135. We sell 135 bushels of corn. They came from the harvested acre. The harvested acre now generates this imbalance. That means we need to impose an acre of planted corn right here. And that brings us back to balance on the transfer row for harvesting corn, but out of balance on the disk. And you can see where this is going. We add the 1, we add the 1, and this 1 acre activity sort of game plugging in lets us go and check that our numbers are correct, because we are generating the expected gross margin. So when we had a 1 acre budget for corn, we generated 171 of gross margin, not including the labor costs, and that's what we have here. Okay, and so we've been able to check all that out, and that's what we want. We could do that check, saying instead of planting the corn, we plant the soybeans. It just makes sure that our multiplication is correct, and also, as we did it step by step, we were able to check our constraints because we were violating them in the sequence that we expected. Right? We weren't getting any free activities in there. So, as I've said, the most difficult part about these is not conceptually. It is in being sure that you get everything balanced up correctly. So looking for some free activity that isn't getting tied back to a resource. So we'll talk about this in a minute, but the production, the marketing of corn only appears in this constraint right here, right? But it's going to be indirectly, so this balance equation, the corn transfer of bushels equation, has to be constrained somewhere, okay? And so it is constrained through these linkages that we just followed all the way back to the planted acre assumption. And so that's what we want to be sure that we're not missing out on. Okay. So, and that's what these notes down here at the bottom say. So you have this spreadsheet model given with this lab. So a couple of notes. So these empty cells, Excel is going to treat as zeros. And then every activity up here has to be connected to a resource constraint. Okay, you don't want any free marketing going on. And so either it's going to be directly constrained, in this case, the activities that use labor will be directly constrained by the labor constraint. The planting activities will be directly constrained by the land constraint, and then the other activities will be indirectly constrained either by land or labor or both. Okay, so this is a little different than we developed the model last time. We put the planting of corn, soybean, and wheat as the directly constrained row, and now we're just saying that in addition to using this land, that land had to be prepared before, and so we just kind of work backwards and make the plowing and the disking there. Those are now transfer rows. So you have to plow before you're allowed to disc. You have to disc before you're allowed to plant. But planting now draws directly on the 600, and you'll see that that changes a little bit the way we see the sensitivity information. But in practice, nothing is different. Okay, so yeah, just to run through that. So planting activities are now directly constrained. Harvest activities are indirectly constrained by the land constraint. The marketing and sale of crops are indirectly constrained by the land constraint. It takes 2 steps to get there. First, you have to move through the transfer of crop bushels, and then you have to move through the harvest linkage. How would you describe the following being constrained? Plowing and disking. Well, plowing and disking are cost activities, right? They generate nothing. They just generate costs for us. So we would avoid them if we could. But they are indirectly constrained by, well, one, you'll never do them more than the amount of land, but they're indirectly constrained by the requirement that land has to be prepared. So this treats them much more like an input demand for the labor and the cost, the variable cost that has to be done. You want to produce something and make some money, you have to incur these costs, and we'll treat that as a linkage or as a sequence constraint. So they're constrained. They'll never exceed 600 because the land constraint tells you that, but they'll always be equal to the total harvested land because there's no way to avoid these costs in the model. Okay, this is what the sensitivity is going to look like. The activities, so the solution values, and the sensitivity on the variables. We see a solution that we've had before. So you you plow and you disc everything, and then you get this corn soybean split. What's new is you move down here to the bottom, and you get sensitivity information directly on the harvest sale of corn, harvest sale of soybean, harvest sale of wheat prices. Okay, so these are per bushel prices, 260, 635, 370, and these allowable increases and decreases are telling you how much the price of corn and soybeans can go up or down before you change the solution. So all of our budget information that we would want is now directly in our model. You can see it all right here. So that means our sensitivity, our range analysis over here, the allowable increase and decrease, includes everything. So the one time we played with this before, we were looking at the wages for hired labor and family labor as the internal wage. Now we have crop prices per bushel prices here. So let's just look at that. A new solution will be generated if the corn price falls by a penny or increases by 3 pennies. Soybean price falls by 2 cents or increases by 7 cents. We'll get a new solution. And then not for the what, but for the wheat price, you need large changes in the price. So these are on the order of you need something close to a 8 or 9% price increase compared to these very small 1 or 2%. Yeah, so let's proceed from that, and just remember what parametric programming is. So I want to be a little clearer than I have been. Parametric programming, when we don't use the range information, means just varying some parameter to try to trace out the economic relationship between a quantity and a price. It could also be between 2 quantities. It's really just it's trying to trace the relationship between an exogenous piece of information and an endogenous piece of information. That's probably the best definition I can give you. So, if you were to look at it from the perspective of the land constraint, the quantity of land is what's fixed, right? That's the parameter. That's the right-hand side. And so we fix that at 600, and we expect land demand to be downward sloping. So we could do something where we change the parameter, the right-hand side of the land constraint, and then we track, endogenously, we track the shadow price for land. Okay, and so if we use the information that came out of the sensitivity report for land, we would see that between 0 and 561, the shadow price for land is 171, and we didn't have the sensitivity. The constraint sensitivity wasn't shown there, but if you run it and run the model and see this is also from the book chapter. Between 561 and 667, the land shadow price drops to 169.42, and then above 667, you end up with the shadow price falling to 155.45. Right. So as you get more land, the marginal valuation drops, and then above 1,019, the price falls to 0. So what's happening there? Well, it must be the case that we no longer have enough labor to plant more land, right? So land becomes slack at this value. And so when we're talking about parametric programming, it is really about finding these endogenous values, the shadow price of land in this case, 171, 169, 155, and 0. Finding all of those that exist in this linear programming model. So if we were doing a nonlinear model, right, a smooth, continuous model, the land price and acreage relationship would be some kind of curve, or could be a straight line, I guess, but it would have some kind of curve to it. But in this case, we're only able to generate a few different solutions because this model has corner points. And so this is what it looks like. This is the parametric program, or the parametric land demand curve that we could generate. The land price at 171. This is the quantity of land that you use. Land price falls. This is the quantity of land that you use. Add more land to the model, and the shadow price falls here, and eventually you get to a point where it has no marginal value because you can't use it. And again, I want to be clear that it's not because it's in this setting, right, that you can't use it because you run out of available labor, right? And we're only changing one thing at a time. So we're changing the right-hand side, this axis here. Add more land, and you get these responses in the shadow price. Add more land, you now get no more response because you've hit something else. Something else is the most limiting factor, and it's causing this pricing to go to 0. Okay, so let's just changing parametric programming would follow the same exact result. We can use something like the range results on a constraint to say, where should we hit our targets? Okay, we know between 0 and here the price is going to be the same, and so we just need to be able to identify that shadow price, this shadow price, this shadow price. And if we were doing it for what we're going to do in a minute, we're going to get out of the land demand function business and think about the corn price sensitivity. Then we're going to change the corn price, and so then we'll have a price on this side where we think about not feasibility but the internal response, and over here we'll be looking at the quantity of acres that we want to plant. Okay, so parametric programming is changing a parameter iteratively to build the full sensitivity of the model to adjustments. You solve a model once and you get this range analysis that says the price can go up, the price can fall, but it doesn't tell you what the new solution is going to be for some variable you're interested in. And it doesn't tell you about the next change that may occur if you keep expanding or keep contracting some value. And so that's what parametric programming is. It's trying to sort of examine the full space, the full response that exists in your model to some changes in a parameter. And it has to be done one at a time. Or you can do them in sequence. You change one, and then you change the base assumption, and then do the parametric adjustments again for the same one. That would be the shifting case that we've talked about. So the classic parametric programming problem is build a supply function that summarizes the response of an output choice to changes in its own price. So it's just a supply function or a supply schedule holding everything else constant. So we will generate the corn price, or change the corn price, generate all the quantity changes of corn, and we'll have a supply function. We expect the supply of corn to be increasing in the corn price, but the constraints aren't changing. So something else has to be adjusting, right? So it must be the case that corn price adjustment causes us to shift resources away from something else and bring them into corn production if we get that increasing return, or if we get that sort of upward sloping supply behavior. We can also track cross-supply behavior. So how does soybean output respond to corn price changes? We know in the base solution to this model that there's a mix of corn and soybean produced. So if corn price goes up, the ratio of corn to soybean returns are changing. If we expect corn planting and harvest to increase, it has to come from somewhere because the constraints are fixed, and it's probably going to come from soybeans. So we want to see what those trade-offs are. If we go back a couple slides here, we could look at the corn price, and we've already talked about it. So 260, take away 2 cents, add 3 cents, take away 1 cent. So the increase and the decrease, then that gives us the ranges that we would want to think about. And so that's what I do here. I take away 1 cent to 259, add 3 cents to 263. And so in this case, we have a pretty small model, right? If you go back and look here, this model has 1 resource constraint, 2 resource constraints, 3 resource constraints. So it's a very detailed model, has a lot of sequence information in it, but it only has 3 things that can actually cause you to bump up against some hard limit in this model. And in fact, in the base solution, this is the base solution here, there's no hired labor, so you're kind of stuck with just a couple of different corners being generated in this model. These are the 2 sort of binding pieces of this model. So you've got some slack here that you could use to expand production as needed if returns go high enough. But you know, this is a pretty simple model in terms of corners right now, and so that's why you only see a few different ranges being built into this supply function. If you had 100 constraints, you know, weekly labor constraints, or 15 types of land, right, then you would see a lot more potential to build in corners, and those corners are directly related to how many sort of kinks you get in this supply schedule, or this demand schedule here, or the supply schedule we're going to build. Okay, so we might just say, in general, the expected relationship between price and quantity that we're going to generate, if we were to think about the price of corn versus the quantity of corn, we would get some positive relationship. We're going to think about some other price, some competing price in the model. As that price, we would expect that to be an inverse relationship. So the price of soybean needs to fall, right, all else equal, for us to think about expanding corn production. And so those are the things we might check. So we're expecting inverse cross price behavior, positive or direct relationships between own price. This model is very sensitive to changing to pricing of corn and soybeans, right? Those are very small ranges. So we also could have anticipated that just from looking at the budget analysis and the work we did last week on the labor, because the model only differs in labor usage. So there's not a lot of sort of play among activities. So the pricing between corn and soybean is very close when you look at the gross margin. And really the soybean advantage in this model comes from being labor saving, right? And so to the extent that you don't want to hire outside labor, soybeans gets used to conserve family labor, which we have a marginal value of 0 for because we don't have any other way of selling it. So I do want to just be sure that you are in your mind setting aside that the labor analysis we did last week, because right now we're saying the family labor either goes to the farm production and generates some return or it sits idle. Okay, and that's because it just makes it simpler for us to consider. Okay, so the things that are in play here, the things that can cause things to adjust, the corn price, changing the relative return between corn and soybeans, and then shifting in labor usage. Okay, so the model only differs in labor usage, so there's a narrow range. A small drop in the corn price below 260 causes the corn acreage to go to 0. Okay. Then when the price reaches 260, you jump over here and you produce 354 acres. Another small increase in the corn price causes you, it makes up that small difference in the labor usage, right? Because labor has a pretty small marginal valuation in this model, that family labor does. It causes you to shift over and then start to plant only corn, right? So the shifting here goes from 0 corn planted at 259, 354 planted at 260, and then over here at 263 we plant everything we have to corn. So this is a dot model. Okay, so those are the sort of 3 points that are relevant. So 0 at 250, below 260. Between 260 and 262, we're going to plant about half or more than half, and then when it gets above 263 or above, we're going to plant everything. That is our supply schedule. And then up here you see that we're tracking the soybean quantity at the same time. Everything that isn't planted to corn goes to soybeans. Soybeans is reduced when the corn price moves up. Soybeans reduced further. In fact, we're not planting any when the corn price gets at its at this trigger point, 263. So anything above there, that's all we're doing. Okay, so the corn supply function represents price and quantity under constant conditions. Okay, so it's important for us to keep in mind that it's definitely an all else constant situation. So we would ask ourselves, what if the soybean price changed, right? So if we go back here, we know the price of soybean changing has a relationship to the quantity of corn. And if it is an inverse relationship, then a price of soybean going down, causing us to be expansionary in corn, means that we would be shifting. So this negative relationship here means a positive shift. If you have this, if this is your corn supply curve, and this price of soybean falls, you shift right. If the price of soybean increases, right? So as soybean price increases, you retract the quantity of corn. It must mean that this is what happens when the price of soybean goes up. So you shift to the left, you shift to the right when soybean prices fall. Okay. We can do other things. What if the land supply changed? What if the price of hired labor changed? Okay. This one would be interesting because it has to get pretty low to be competitive. Any of these could show up in our supply functions, but they would only show up as a shift. We would need first to have identified this as the supply relationship, the supply curve, and then think about what kind of shift up or shift down we get when we vary some other parameter. So the range for those variables, so when you build out your supply function, they tell us how much something else can change without shifting our summary supply function. So if this is the summary of our model in terms of corn supply related to its own price, this acreage versus this price, then you could look at these simulation results and think about the simulation results and think about the plus minus to the soybean price being how much allowable increase and decrease is there before you get shifts to your supply function. And so that's what we do. So let's first, this was our base model. No, sorry. Okay, sorry. These are backwards. So, yeah. So the point here, we're trying to lower. This is our base assumption, right? So this is how the corn price versus quantity schedule was in our solution we just looked at. So this should say 635. If the price, and 630 it has the same price, but if the price falls of soybean down to 628, then the corn price schedule shifts right, okay? And so that means that the corner points between corn and soybean stay the same. The schedule looks the same. It's just now you need lower corn prices to compete. So this is when the soybean price is 628. Sorry about that. And so you get that shifting down. So let's look back at our graph where it's easiest to tell. So this is our base solution. And if the soybean price falls, if it falls by enough, then soybeans are less competitive. And what it does is it just lowers these trigger points, these adjustments for corn, because corn now doesn't have to be as valuable per bushel because soybeans aren't as valuable per bushel, right? And so you get the supply schedule shifting to the right, right? So it's expansionary in that context, because lower prices now will cause you to move over, and that's what's trying to be done. So sorry, this should say 635. Doesn't matter what it says. This should say 628. So we shifted the supply curve down, to expansionary. Quantity values are the same, and so that's the real point that I guess this slide is trying to make. It's probably why I didn't edit it before. So these prices, yeah, let's be sure that we get that right, that these are backwards. But what's really sort of in play here is these quantities and the way they adjust, right? The fact that they adjust together, and these quantities, the values are exactly the same. And so something we haven't talked about enough in this class is that you end up with, because the model's linear, and that means the constraints intersect, and when you have linear constraints, and you end up with these corners in the quantity space, you end up with something called the basis, okay? And so what you really have are, some people in sort of more advanced classes, they'll basically just talk about the number of bases, right? That's the plural of basis, the number of bases that you generate in an LP model, and you can predict the maximum number based on the number of constraints with non-negative right-hand sides, okay? And so you need to be able to generate these corners to generate behavioral changes in response to parameters. So when I went back up here and said we have relatively few right-hand side values, I was talking about that because that means you're going to have very limited options or very limited quantity responses because there's only a few ways to change the basis of this model. Okay, and so that's what we end up with. It's possible we could have a ton of activities that are all very sensitive so that you switch, right? So a third activity, a fourth activity, a fifth activity. So it's also related to the number of activities and how close they are to one another parametrically. But in general, in this kind of problem where we're thinking about sort of broadly as crop alternatives, we're not going to be changing the basis in terms of the corners of the problem. We're actually just changing the scale, right? And so instead of being 259, 260, 263 being the relative parameters that cause us to change among basic solutions, these are three basic solutions. We haven't changed their physical presence, though, their physical relationship. And so we're just going to be changing the scale of this parameter that causes us to adjust in the basis. So minus 3 cents all the way across, and we'll get the same basic solutions just at a different scale of the parameter. This works a little differently when you change the right-hand side. Okay, you still are constrained. You still are going to get relatively few basis changes. But you are also changing the availability of the problem. So it depends on really the number of constraints that are binding and aren't binding, because the expansion of one constraint eventually will lead to something else, a new basis being formed with a constraint that was previously not binding. We're not getting that in this price analysis. Okay, so if you need a better handle on this, this is not something, it's basically been absented from all linear programming books, but I want us to understand that this is a feature of the linearity, that these quantities being the same, or sorry, the pattern of quantities being the same. The more constraints you have, the more chances you have to generate corners. That's really all I'm thinking about. All right, so if you add constraint after constraint after constraint, we even drew this. We said you could approximate a curve function by joining a bunch of chords and segments to make something look like that. Now in practice, it's very difficult to get a sort of a set of quantitative relationships that would make that smooth approximate function. Yeah, and I guess the point is we have lots of constraints, lots of detail here, but most of them are balance or transfer equations. And since those tie directly, they indirectly tie back to the resource constraints to generate limits, they're not corner point. They're not important to the basis. They can be substituted away. Okay, so we'll just continue this implementation. So that's everything we have for today, except for your assignment to work on some things. But I want to go through a GAM setup for this problem that makes it a little easier to do parametric programming analysis. So you're welcome to answer your questions this time in Excel. You've already got the Excel model there, but I'm also going to post this GAMS model that you can use. And so I want to talk about how you would build these same experiments, these parametric programming experiments in that GAMS model. How would you go about getting these price changes and collecting the results? Okay, so I think I've talked about this a few times already. I like to build models in spreadsheets, generally write them down. You can either use that sort of Tableau setup from Kaiser and Messer, Chapter 4. You can see that big table they use. They number their equations, they give variable names, and it's ready to program directly. But I tend to just like to write the mathematical form of it, the equation form of it. And so if you were to do that, you would have something that looks like this. Just define the coefficients in the objective equation as Ci, let Xi be all the choice variables. We call it the A matrix, the full coefficient matrix between activities and constraints is just Aij, and then B sub j are the right-hand side coefficients, so the limits on the model. We have a bunch of transfer activities, so a lot of the B sub j's are going to be 0. We have a maximization problem. This is the equal sign in GAMS, remember, for an equation. We're going to sum over the activities, the objective, either cost or return, times the activity level, and then in each constraint we're going to sum over the activity, the A coefficient times the activity level, less than or equal to B sub j for all j. Okay, so in the GAMS program, at the top you'll see that I have put in a couple of sets that include all the activities in the model. So I call it ACT. So it's plowing, disking, planting, harvest, harvest, hiring labor, selling, harvest, sale, and then all the boundaries in the model. So every constraint you're going to have needs to have a right-hand side value. So planting, family labor, transfer of corn bushels, transfer of soybean bushels, transfer of wheat bushels, hiring labor, plowing, disking, transfer of corn to harvest, transfer of soybean to harvest, transfer of wheat to harvest. Okay, those are all, everything with an X, I believe. I use X for transfer, XFER for transfer, and so I do that because I know that I want to put a 0 in the right hand side. Okay, those have to be balanced out. Oh, sorry, plow and disking are also have zeros on the right hand side. I'm treating those as transfer activities as well, but I did not put, it's probably bad form. I probably should put XFER in front of those just so I know what to do. But anyway, I got it right. And here are the coefficients. So $10 is the variable cost on plow, and same on disc, and then the variable cost for planting, variable cost for harvest, the higher labor per unit, and then you don't get any positives, no returns, until you get to the harvest sale. Okay, so when I started this looking in the Excel model and I said let's sell a bushel of corn, it's really the starting point from the model, right? The choices say, okay, I need to generate some returns to maximize this. Let's check over these positive activities, and then these positive activities work through the transfer rows and the constraints to pull in costs. Okay, and so if we had messed up the plowing and disking transfer, it would be possible that we were out there saying let's plant and harvest but not doing the land prep, and so that's where those get pulled in as well. The A matrix, so just like Excel, GAMS will ignore if you leave a blank, and so this is the same tableau. I like to put all the activities and constraints into one big A matrix. It's a little easier than you might be interested in building up matrices for planting and harvesting, or for the crop activities versus the hiring activities. That's fine, but you just know that if you build some submatrix over here that's on the planting and it only deals with those constraints, you're still going to have to fill in all the zeros. So you'll either need to make a coding introduction that sets all those those additional matrix elements that you don't care about to 0. You just need to do the parameter assignment. Okay, and so then how to do the experiments? Well, I want to open the code and walk you through it top to bottom in a second, but I'm just going to make changes to the objective coefficient. Okay, so you'll see here that when I want to solve this model, is called Kaiser-Messer Chapter 4. When I want to solve it at a price of 260, I just make that price assumption right there before the model statement. The model now uses that value for the price in all of the equations that I'm using, and then it runs the maximization, gives us the solution, and then down here I want to make a change to the price assumption. So the objective coefficient C for harvest, sale of corn is now 270, so a 10-cent increase in the price. GAMS reassigns those values, now reads in all the equations and solves. You'll see when you get to the actual code, this was probably snipped out before we did it. Actually, to keep them in order, because I know roughly what the basis changes are in the prices, I think I used prices 250, 260, and 270, and so the first experiment is actually KMCH41, so it's chapter 4, experiment 1, experiment 2, experiment 3. So lowest price, second lowest price, third lowest price, because we're no longer saying we have some base assumption for price, we're saying we have a range of prices we want to consider. Looking at those two experiments though, 4.2 and 4.3, these are the results you should get. So the harvest level or planting level, whichever one you want to think about, the harvested acres of corn, harvested acres of soybean, right there with what we expected. This translates those into bushels down here. If you want to know what the 135 times bushel per acre is times this, that's what you get. When that price goes up, right, the price of corn goes up, that objective coefficient goes up, what happens? Well, we know, because we've already done the parametric programming for this, that it's going to be all corn production at that level. And so when that price goes up by 10 cents from here, we shift and we do a wholesale shift. We move everything that was being planted and harvested as soybeans into corn production. So we can compare these results directly, or as we've done before, we can collect our results, right? So if we're interested in the harvested corn, harvested soybean acres, as the price changes for corn, then we would just create a parameter, something called the, I don't know what it's called, create some parameter and record results every time we run a new solution. Run this experiment, record the harvested acres of corn and soybeans. Run this one, it's the second trial, or the third trial, I guess in this case, record the harvested acres of corn and soybeans. Okay, so we're interested in collecting information about crop acreages. That's the design of this problem as we change the price of corn. So we're running 3 experiments. So I need a GAMS set that is just going to look at the harvested acreage activities. So let's go back to our initial setup here. And remember that the set activities is every set, or sorry, it's every activity in the model. Plowing, disking, planting, harvest, harvest, harvest. Well, I only want to look at, when I record things for my parametric programming results or my solutions, right, as I change one of the parameters. That's all we're doing, right? Maybe parametric programming is not a great name for this, but somebody named it that. But the idea is I want to vary this parameter for corn price. I want to record all these solutions when I vary it. But I only want to know these 3 things. I don't want to record every result in this model, because as you've seen, these are duplicated. These duplicate, right? Those are the same thing. These bushel results are interesting, but they are just a coefficient for yield multiplied by these acres. So that's not that interesting. And then the plowing and disking is not interesting at all, because as long as you're out there planting, as long as the land is generating returns, those are just stuck at 600 no matter what the prices are. They are invariant quantities to the prices. You have to have basically every crop in the model get cheap for you not to want to plant. So what I really want is to be able to siphon off these 3 activities that are harvest activities and make a new set. And so that's what I'm going to do here. So the activities, ACT, is the full set of activities, but only 3. HC, HS, and HW are harvesting acres activities, right? So those are that is the, after planting, we choose to harvest those. So we could think about that being a subset of a superset called activities, or ACT. And so it if you these three are all contained in some broader set act. And so what we need is a way to do a subset in GAMS. And it turns out that GAMS has an easy way of doing that. It just says, write your subset, and then in parentheses, put the set that they all belong to. Then list the elements, and they need to be in the same order. I'm pretty sure I didn't write this here, but as memory serves, they need to be in the same order as they appear in this set, ACT. And so I've obeyed that here. So we declare the subset. So we're using a set statement, put the new name for the set. I'm calling it crop acre. And then in parentheses, put the set that they already declared that they belong to. And so I'm saying I want to build a new set. I want it to be crop acre. I want it to be a subset of ACT. And then here are the elements that I actually want to be to be included in my subset. So harvesting corn, soybean, and wheat. Close that off with a parenthesis or a semicolon, and that should work. That means that I can make a new set called trials, trial 1, trial 2, trial 3, and then I can make a new parameter called the acreage reporting, and it'll have elements trial and crop acre. Okay, and so run an experiment here. It says use an assignment to change the price assumption. So I'm going to set the price first at $2.50. I'm going to call that model KMCH Kaiser-Messer Chapter 4 Trial 1 model. Remember, you have to change these models to resolve it. Use all the equations, solve it, and then for me, in the acreage report, we're going to assign the variable levels for crop acres. Right, so that takes the activity level for HC, HS, and HW, the level, .L, and sticks it in the first column of the the first row of the acre report. Run it again. The second experiment is increase the price by 10 cents. You can see that I'm just using 10 cents because that will cover all the basis for this model. So 250, 260, and then I think the last one is 270. Set the price to 260. Change the model name. Be sure that we're solving this new model name that we just gave it. Record the results in trial 2. Okay. So now let me pause and switch out to show you the GAMS code. I'll scroll through it real quick. Okay. So this is the exact code that I'm posting. If I find something, I know it runs. It's a bigger model than this. You'll see here that that comment doesn't belong, so it may not be in the one you get actually. So we're going to do an extra. You'll have some lab tasks that you have to do to sort of finish this. You can do them however you want. But one of the things we'll continue talking about is how you might do something that's build in some adjustments to the yield parameters. So this is the Chapter 4 Kaiser-Messer model. So the activities all in a set, the boundaries give you the equations, right? So you have the boundaries here, the activities here. That's that A matrix. I just call it the A matrix as a parameter name. We need to set the right-hand sides. So you have all of those. We need to set the objective equation coefficients. We got those. And now we need to do our variable declarations. So there's an X for every element of the set activities, and then there's R for the objective equation. So this is the return variable. These are the activity levels, X. The non-negativity constraints are on X. That's what the positive variables for, remember. And then for the equations, we're just going to call them right-hand side. Those are probably not a great name, but that's what we're going to do. So this is everything with a right-hand side on it, and then there's one for each element of boundary, that boundary set, and then we'll have the objective equation. So the right-hand side equation set looks like this. sum over activities, A matrix times X less than or equal to B, and then the return equation. Yeah, and so I've already built this subset in for you, so you don't have to worry about getting the syntax right, but observe it. Be sure you get it, you understand what's going on. So this is a new set. It is within the activity set, and it only contains these three elements. So now we declare our trials, the three trials, and then we declare our parameter. For every trial I run, for every element HC, HS, and HW of crop acre allocations, I want to generate an acre report. And the price is 250, 260, and 270. I want to know what the planting for corn, soybean, and wheat are, and that's what you would get. And if you run this, yes, go all the way down to the display, you'll see that we are getting what we expected here. Okay, so let's go back to our PowerPoint one last time. Let's see what's at the end here. It's your lab task. So for November 14th, what I'd like you to do. So first task, how does the hired labor quantity respond to changes in the corn price? Okay, so you just ran you just ran the basis solution, right, for all three bases that exist in this model as we've seen them. So you can just look at the solution that we just generated that's already in the code, or that will run with the code you have, and look at what would a labor supply schedule, or labor demand schedule look like relative to the corn price. Do we ever hire labor? That's what that's asking. And when do we do it? What price of corn will cause us to do that? Right? And so because we're using the allowable increase, it's going to be so far back, isn't it? Sorry. Wow, sorry. But because we're using the true sort of allowable increase and decrease for the price of corn, then everything we do, right, it just matters that we're getting outside of these two ranges. So you see that I'm lowering the price by 10 cents and then increasing it by 10 cents from the base assumption of 260. Well, we've already done enough analysis on this model just by looking at this, right, to know that we've covered the basis of this model, right? So it's not important for us to sit there and come up with some really fine, even if we switch to not thinking about planted acres and instead thinking about hired labor, I just want you to understand that these prices are still the right price points to check to see how labor is adjusting, because it's just going to be a flat spot, right? These price adjustments from the allowable increase and decrease are good enough once we get to this point and see that they're all or nothing. They are good enough for us to get the full range of flexibility for the corn price. Okay. Now, if we switch to some other parameter, it may have more. It may have more adjustments. Okay, so do that one first with the code is there. Download it, run it, and then check on this hired labor quantity for me. You can do it with your own build a parameter, or you can just scroll through the solutions, however you want to do it. And then I want to do a new task. So I want you to consider the corn price change model again, right? So this is, when I say parametric programming, in this case I'm saying change the corn price around, make the adjustments to the corn price that are required to see how harvested acres change for all crops in response to corn price changes. So I want you to do that same work we just did on the corn price versus harvested acres for all three crops, using one assumption where all the yields in the model increase by 10%. So you can do that however you want. If you want to try to do it in GAMS, in a clever way, programming way, go for it. But Um, just, be careful, and maybe even check your work in a spreadsheet to see if you're getting what you expect. But it's the right way, or the sort of right way to do it for comparison points, I guess. But you can do it however you want. So do it first by increasing all the yields 10%, so you have this sort of innocuous, well, we shouldn't call it innocuous, we should call it unbiased, I guess, yield improvement across whatever you plant. And then in the second one, we're going to put some bias into the sort of technology growth and say that in assumption set 2, corn yields go up by 5%, soybean yields are unchanged. So we don't get any technical boost there, but wheat yields increase by 15%. And so then I want you to, for both of these assumptions on yield, report the acreage of all crops versus the corn price schedule, okay, for both of those scenarios. So what does that mean? Well, under this assumption set and this assumption set, you need to check and make sure what prices of corn will cause shifts in the solution. So you need to do some range analysis. And then you need to generate all the solutions over the prices that are in the different boundaries, that are in the different parametric ranges, and report those supply schedules, and bring your results to class on November 14th, and we'll go through those. We'll talk through those and think about what kind of model we have here, and what kind of response we're getting. Okay, and we'll think about what other questions might be relevant to something like changing these yield assumptions, changing those price assumptions. So what kind of experiments would be important there? Policy experiments, technical change, right? What kind of sensitivity to not just the core numerical assumptions, but the core economics environment, policy, and technology. Why are we doing this parametric programming? So that's what we're going to try to talk about on Thursday. It's not just, hey, we could have the numbers wrong. We know how to deal with questions like that, but hey, what if the economic environment is one that's adjusting, and one that we want to build our model and conduct our analysis in a way that we understand not just the core solution, but also how we expect adjustments away from that core solution. Okay, with that, you've got some tasks here to play with, work with somebody else if you want, this is our discussion topic for next. Even if you have trouble getting this done, getting this to work, you should be able to do it in the spreadsheet if nothing else. If you have trouble getting it though, at least put down your a priori, right? What do you expect to be the change in this one versus this one? But do your best. I'm not going to take it up for a grade. It's just the thing I'm getting ready to talk about next are these experiments, and I would like to do it in a semi-Socratic way. Okay, thanks for your attention. This was a pretty long one, but your code and spreadsheet are sitting there, and you're ready to go.